Thanks very much. So today I'm going to talk to you about how to build a driverless race car using deep learning. I guess I should start out by saying that this was a personal project. So by day, I am co-founder and CTO of Overleaf. If you don't know what Overleaf is, we are Google Docs for scientists. So we do online collaborative editing, but specialized for scientific papers. Today we have about 3 million users. But here's the big transition. Our first users were John and I on a driverless car project. So we worked together on the Heathrow pod, which was the world's first computer-guided taxi system. It launched in 2011 and is still running at Heathrow Airport. So if you're ever at Heathrow, you can go to Terminal 5 and get a driverless taxi out to business parking and back. If you're ever at Heathrow and you have some time to kill, it's a very fun thing to do. So the thing that allowed us to do this way back in 2011 was that the Heathrow pod was all on its own infrastructure. So it was a closed system, and we could use, and we did use a fairly sort of traditional systems engineering approach to design this system and prove that it was safe. And we could do that because we controlled the whole thing. But most research in driverless cars since then has been about getting driverless cars to work on public roads, where you have to worry about pedestrians and other vehicles and cyclists and all sorts of messy things like that. So some of the pioneers in this field include this guy, Sebastian Thrun, who used to be a professor at Stanford, who won one of the big DARPA grand challenges to design driverless vehicles. He left Stanford and founded Udacity, which is an online sort of education provider. They do MOOCs. And because it's founded by Sebastian Thrun, they did one on how to be a self-driving car engineer. So in my copious free time, I decided to do that course, and it was really good. I'd recommend checking it out if you want to do it. And today I'm going to talk about one of the labs in that course. So the lab was based on this paper from NVIDIA, which came out in 2016. So what these guys showed was that you could take a camera image from the front of your car, feed it into a convolutional neural network, which we'll talk about, and it would output a steering command. So just like you look at the road and you decide, do I need to steer left or steer right? They were basically doing the same thing with a neural network. So what makes this remarkable is that it's very different from the systems engineering approach that most people were taking and are still taking to driverless vehicles, which is, you take your camera image and you'd run object detection and you'd run some planning, all sorts of different subsystems that would interact. But this approach, actually, you just train one big neural network, and it just kind of magically works. So the assignment was basically to reproduce this. And this talk is just going to go through the steps that we did to complete this assignment. So they provided a simulator, so we didn't have to do this for real. That would be quite unsafe. So we basically start by just me driving the car around in the simulator, collecting some training data. Then we're going to feed the camera images and the steering angles that I produced when I was driving around into a deep neural network to train it. So basically, it's going to try to imitate me. And then we're going to plug that network into the car and let it drive itself. Or not. We will see. It's also worth saying, so in the middle here, I'm going to talk a little bit about the theory, and I'm going to hand wave a lot through that. So if you already know a lot about convolutional neural networks, you may find that boring, or it may make you angry. But the rest of you hopefully will find it interesting. Right, so let's start with some training data. We're going to start with our first video, internet permitting. So you can see up in the top corner there, we are recording. And I'm just trying to drive in the center. While I'm doing this, we are recording camera images at 10 times a second and also my steering angles. You might also notice that I'm not very good at this because basically the only way to steer this car is with the left and right arrow keys. So it's not very easy to do. OK, so let's try to go to the next slide. There we go. So the first thing we have to do is to clean up the steering data. So the blue line is my actual inputs. So you can see it's very spiky every time I press a key. And the red and the green lines are two different smoothing algorithms that we can use. And we'll basically try both of them out and see which one works better later on. But that was hurdle number one. Hurdle number two, we can get that playing. If we only ever drive the car in the middle of the road, then it will never have any experience of how to get back into the center if it ever does get off track. So what we have to do is also to record some recoveries where I stop the recording, drive off to the center of the road, and then drive back to the center of the road with recording on, stop recording, drive back into the middle again, and just try to teach the car basically how to get back into the middle of the road if it does find itself off on the sides. Okay, so let's go to the next slide. So we do that, spend a lot of time driving around in the simulator. I collected about 11,000 frames of training data, which in some sense is, reasonable amount of data, but in the world of deep learning, it's not very much at all. I think we would struggle to train a network from scratch using just 11,000 training points. So how do we get around that? We use a technique called transfer learning. So basically this means we're going to take someone else's network and we're going to repurpose a little bit of it to do our task. So the network we're going to use is called the Inception v3 network. And this is a network that was trained by Google to compete in an image classification competition. So basically you feed in an image over here and it runs loads and loads of computations on it, and at the end it spits out a class for the image. So if you feed in this one, it'll tell you that's a Siberian husky. If you feed in that, it'll tell you it's an Eskimo dog. So some of these classes are quite fine, which is interesting. So this is a huge network. It has 25 million parameters that Google has lovingly trained. And so how would we go about building on that? The answer is, it turns out to be really simple. Basically, we kind of lobotomize the network, and we just chop off the first bit. The reason that works is that this first sort of few layers turns out to be relatively generic image processing stuff, so edge detection and looking at textures, things like that. And then all the rest of that network was the bit that encoded the difference between Siberian Huskies and Eskimo dogs and all the other classes. So all we're going to do is we're going to take this prefix and then we're going to tack a couple of little layers for our own application on. So we only have to train this little bit, and we're going to use this huge thing that Google already trained for us. So that way we can hopefully get away with much less training data than we would need if we started from scratch. So how does this work? Basically, to build a convolutional neural network, which is the kind of network that this is, you need 3 building blocks. So the first one is convolution. The second one is resizing. Basically, we're just going to squish the images down. And the third one is called an activation function. So I'm going to go through those 3 things. I'm going to take in as an example this single frame. So basically, as we're driving, we're going to get a frame like this, which is 320 pixels by 160 pixels. We're going to run it through this network. And at the end of it, we're going to get one number out for that frame, which is how much should I steer. So we're going to see how we use a convolutional network to get from this rather large image to one number. So convolution is the first step. So convolution is it's really quite a simple idea, but also very general. So what we do to use convolution is we define what's called a kernel. It has many names, but I'm going to call it a kernel, which is a small matrix of numbers. We then take our kernel and we line it up with the pixels of the image. And then for each pixel that overlaps, we multiply the pixel value by our kernel value. So this is going to be 0 times this, 0 times whatever it is, 0 times that, 0 times that, 1 times that. That's exciting. And then zeros for the rest. And then we add all those up, and that's the result. So the identity kernel is a really boring kernel, because all it does is basically just copy this pixel from input to the output. Once we've done that, we start sliding the kernel along the image, and we just repeat that process. So this is a very simple operation. It's very efficient. You can do it very fast. But if you ever use like Photoshop, most of the things in the image filters menu will be using a convolution under the hood. And they're just using different kernels. So there's a kernel for edge detection, lots of different kernels for edge detection, different orientations, blurs, sharpens, lots of different things you can do just using this very simple framework. So to kind of build that into a convolutional network, the basic insight is that instead of us very carefully engineering our kernels, we let the kernels be learned from the data. So this little bit of the network, which happens to be the first 44 layers, has 700,000 parameters, and most of those parameters have been trained by Google, and they are kernel weights in those little convolution kernels. And they've already run this on 1.2 million images to train those things. So when we run a convolution with lots of kernels, we basically take one image and we make lots and lots of images. So if we just keep doing that, the amount of data we get expands and we run out of memory. So we also need to start resizing. So every time we do that convolution, usually after a couple of convolutions, we're also going to just squash the image down. There are lots of ways of doing this, but basically it's just like resizing your image. So that's also a very important part of this. So we are going to lose some spatial resolution, but we're going to continue to gain depth. So basically this approach lets us take one flat image that starts with, and then we do some convolutions, and we get some depth, and we squash it down, and we get, and we just keep repeating this over and over again. And we go from one big flat image to a kind of sausage-shaped, quite deep image that's smaller. So that's the end of, or almost the end of the theory. We need one more thing, which is an activation function. So this is where the neural bit comes in. So real neurons are incredibly complicated things with really amazing dynamics and very interesting behaviors. But our very simple model of a neuron is going to be that it has dendrites, which are basically like inputs that connect up to other neurons. And then if all of those inputs add up to some threshold, we are going to activate this neuron, and it's going to pass that on to the downstream neurons. So mathematically, we basically represent that with this really simple squashing function. So if the sum of the inputs is negative, we're going to return a not very large value, so we're not going to activate our neuron. If the sum of the inputs is large, then we are going to activate our neuron. And that's basically the three ingredients we need, and we just repeat those over and over and over again. So it's worth saying that convolutions and some kinds of resizing, not all kinds of resizing, are actually linear operations. So we don't actually gain any power by composing those if we didn't have this little nonlinear step in the middle. But all we have to do is add this one little squashing function, and all of a sudden we go from being able to represent linear things to representing pretty much any function, which is pretty amazing. So that's the end of my theory bit. Let's see how it looks in practice. So if we feed in our camera image, after 44 layers of inception, we are going to get out 256 images for our one starting image, and it's going to be smaller, about a factor of 10 smaller. So instead of 320 pixels, it's going to be 31 pixels and 17 and 160. So I've shown an example, or just a random sample, starting at number 42 here in our stack of 256, that shows some of the features or some of the responses that the network gives when you feed it this particular image. So where these are light, that means the image is kind of, or the network is responding. Those neurons are kind of firing in those places in the image. And if we overlay those with the image itself, we can start to see why that might be useful. So you can see some of the neurons on the sort of edge of the road here in this particular layer are firing. That's a useful thing when you're driving, is to know where the edges of the road are. This one seems to be kind of firing on the middle of the road, which is also useful. It's also picking up some background, but then you've also got like this one who seems to mostly like the background. So you can kind of see that if you combine these different features, there is something useful here, which would be like, where's the road in this image? But we haven't had to tell it any of that. It's just learned all of that. And we didn't even train this bit. This is just Google. So after that, we're now into our little bit of the network. So we're going to run, and this architecture I just made up. There are lots of possibilities here, but this one seems to work OK. We're going to run one more convolution, which is a 1-by-1 convolution, which just means that we're going to basically take linear combinations of all of those 256 features to get down to 64. Basically, we see the same sort of patterns, but they're a little bit brighter, a little bit smoother. And if we overlay them with the images, you can see again, like, definitely we're getting some pretty strong features that say, like, this is the edge of the road. And that's hopefully useful stuff. So that's our last convolution. Then we do two what are called fully connected layers. So here, unfortunately, we no longer get to see what the network is doing, because we're going to take those images and just squash them into one big list of numbers. And a fully connected layer just means that we are then going to choose any linear combination of those numbers. So that means that the input numbers here are the x's, and we're going to train the w's, the weights, for those. And then we're going to do the same thing again in our next hidden layer, our next fully connected layer. And then the final output of that is going to be our steering angle. Also important is that after we do those linear combinations, again, we need to inject that little bit of squashing, nonlinearity, so we're also going to use our activation function after each one of these. So that is our network. Let's time to actually get it to train. So as I've been going through here, there are all sorts of hyperparameters. You know, I've made all sorts of arbitrary decisions. So basically, we're just going to try all the different combinations. So like number of filters in our one-by-one convolution, number of hidden layers in our fully connected layers, different regularization schemes, different optimizers, all sorts of stuff that we can try. But hey, it's just computation. We set it off running it in the evening, and in the morning we wake up with results. This is an example of some of the training data. Fortunately, there are really nice libraries out there that let us do all of this stuff. So this one I use is called Keras, which is on top of TensorFlow, which was mentioned this morning by the Google guys. So these are our 4 layers. This is some technical stuff. The only bit I want to talk about a little bit is the training process. So we're going to keep the inception layers from the beginning that Google trained completely fixed. And then for our 4 little layers at the end, basically all we do is randomly initialize those. So it's going to start out doing really badly. So this loss function is basically a measure of the error between my steering input and what the network predicts. So the first time we run this network with randomly initialized weights, it does a terrible job. It's all over the place. But then we just take the same training data, we feed it through the network again, and the loss drops. We feed it through again, the loss drops. Every time we're using that error signal to refine the weights that we're using so that the network is getting better and better. And after only about like 15 or 20 of these passes through the data, all of a sudden our loss is really small. It's you know, a small fraction of a degree. So it's basically reproducing what I'm doing pretty well. On the right-hand side is the validation loss. It's a slightly more technical point, but actually what we did is divide our training set into 80% training data, 20% validation. And so we know when to stop when the validation loss starts to increase, because that means we're starting to overfit. So we can do that. Let's run our first model with all of that stuff. If you can click the button. So here we go. I'm going to put it into autonomous mode. The throttle is actually just a very simple, basically just always puts full throttle on up to about 10 miles an hour. You can see it weaving a little bit, but it's recovering, but not quite enough. So it weaves a little bit more. And then this time, oh dear, yeah, we lost it. And eventually the car will run into something and crash. So that was our first attempt. So that was basically running that whole grid of models and seeing which one was the best. So now the debugging begins. You know, I made loads of arbitrary decisions in this network. So try lots of stuff, different loss functions. How do you measure the error between me and what the machine does? Different activation functions. We looked at a sigmoid. There are loads of other functions that do the same kind of thing. Different regularization schemes. So this means we penalize the weights if they become too large. It's a common technique. When we're initializing the weights, we can change the distribution we use. Like, just try all these things. This one did actually help. Different layer sizes, different network architectures. There's a lot of things you can try tuning. So after many, many hours of doing that, I found the actual problem, which was latency, which was a facepalm moment. So actually this problem was that because we're using so much computation on my old laptop, it was only able to steer about 3 times a second. So if you imagine yourself trying to steer, but you can only touch the wheel 3 times a second, you can imagine that's quite difficult. So what do we do to fix that? Well, if you buy a faster laptop, that would have worked. But also, we can just take a smaller prefix of the network. So instead of the first 44 layers, we just take the first 12. And that gets the latency right down. So let's see what it looks like with lower latency. Speaking of latency, we were doing so well. OK, so I sped this up because it's a bit boring, and it gets a lot further. So you can see it's not weaving as much. It's pretty much staying on track. It's not perhaps following the best like racing line or anything, but that's probably because I wasn't following a great racing line. See a little bit of shimmy on the bridge here. And then we get to this part, and it gets a little bit confused here. It doesn't like trees. And so it misses this turn, and it crashes. So, but actually, so this one, the resolution to this was basically add more training data. So basically, we just drive around that corner a lot more. But around the same time, Udacity also released a load of training data from someone who had a steering wheel instead of having to do the arrow keys. So also I threw that in there, and that's much higher quality data. Anyway, let's see what it looks like when we've added the new data. Oh, try going back. Let's try clicking that again. So in autonomous mode, you can see it's maybe even a little bit less stable now with all this new data, but it is driving 3 times faster, so that's probably why. This time we make it, we make the next curve, and you can see we're no longer driving off the track. And round it goes. So there we go. That's a success. So the next question is, if you can click me out, great. We've trained our network on one racetrack. What if we put it on a totally different racetrack? What will it do then? So fortunately, they happen to provide another racetrack for us. So let's see how it goes. Put it into autonomous mode. It's starting on a hill, so it has to do a little bit of work. But it's steering. There you go. So it's pretty amazing. So it's never seen any of these data before. So whatever we learned from the previous racetrack, at least within the scope of our simulation, seems pretty good. You can see some trees here, so that's a near miss. But then it recovers. It's okay again for a little bit, but here are more trees. Does not like trees, and that's as far as we get. So still, that's where we got with just this training data. We could add more training data. We could probably do a lot more work and continue working. So what have we done in this talk? So we showed how to take a neural network that was designed to classify pictures of dogs. We repurposed it to drive a car. We taught that car to drive in about 35 minutes of training data. That's a lot faster than I learned how to drive. And we managed to get it to drive for a little while on a completely unseen racetrack. So I think that's pretty amazing. Perhaps even more amazing is that in 2015, no one had any idea that this was even possible, that you could even take a neural network and tell it to just drive a car with no other systems involved. In 2016, thousands of people were doing it on the internet through the Udacity course and in lots of other places. And then this year, I didn't have to do anything. This guy did all the work himself, but I helped put him on the right path. A high school student who did all of this himself with an RC car, doing everything on board on a Raspberry Pi. So that's the pace of progress. So thanks very much. Happy to take any questions.